Okay, thank you very much for the introduction and the invitation to this workshop. It's my great pleasure to talk here. So this is a joint work with Maria-Angel Alfonseca, Fedor Nazarov, and Dmitry Ryabogin. Um, so we completed a solution to this problem number 5 locally some time ago, but recently we realized that we can actually use the same ideas to treat the eighth problem. So I will present both of them today. Okay, so in 1956, Busemann and Petty posed 10 problems about sections of convex bodies in Rn. And the first problem is well known. It asks whether origin symmetric convex bodies with smaller sections necessarily have smaller volumes. Okay. Um, as I said, the problem is well known. It was completely solved in the 90s through the efforts of many mathematicians. Um, but the other 9 problems are still open to the best of my knowledge. So in this talk, we'll discuss problems 5 and 8 from their paper. Okay, so throughout this talk, K will be an origin symmetric convex body in Rn. And let's recall some basic definitions. So the radial function is defined as follows. You have a direction theta on the sphere, and then rho k of theta is just the distance from the origin to the boundary of k. And the support function is defined as follows. You have this theta, you have the supporting plane perpendicular to this direction, and then hk is just the distance from the origin to this supporting plane. We will also need the curvature function of the body k. So if we assume that the boundary of k is C2 and has positive curvature, then the curvature function is just the reciprocal of the Gaussian curvature at this point. And this is the point of contact of the boundary of k and the supporting hyperplane orthogonal to theta. Okay, so more generally, if k is not smooth, then the curvature function can be seen as follows. You have the surface area measure of k. So if it's absolutely continuous with respect to spherical surface measure, then its density is this curvature function. All right. So let's now state these problems. So problem number 5. I will use this notation. Theta perp will be just the hyperplane passing through the origin orthogonal to theta. Okay. So problem number 5 reads as follows. Suppose you have a convex body K in Rn such that the product of the support function in the direction theta times the area of the section of K by the hyperplane theta perp. So if this product is a constant, doesn't depend on the direction, can we say that K is an ellipsoid? Okay, that's problem number 5. Problem number 8. Again, we have a convex body such that the curvature function is proportional to the area of the central slice perpendicular to theta raised to the power n plus 1. Again, if we have a constant c independent of theta, can we guarantee that k is an ellipsoid? Okay. So let's make some observations regarding these two conditions. So if you look at this first condition, so what do we have for Euclidean balls? So for Euclidean balls, the support function is the same in all directions. These sections are also the same, so this product is a constant. And same here, right? The curvature function is for the Euclidean ball of radius 1, it's 1. Sections are the same, so again, this is true for Euclidean balls. Now, what happens if you apply a linear transformation? So if you have a body K that satisfies this condition 1, then one can check that the body Tk, where T is a linear transformation, then this body also satisfies this condition 1, but with a different constant. You'll need to multiply this C by the determinant of T, right? And similarly for this condition, if K satisfies this condition, then so does a linear image of K with this constant, right? So this means that these conditions are also true for ellipsoids, okay? So let me at least try to justify why this is true, this condition true. So let me show this picture. So problem number 5 has a nice geometric interpretation. So what we do is take a theta, take the section perpendicular to theta, here it is. Then take the supporting plane parallel to this section. Here you have this point of contact. And then just construct this cone with this vertex and this base. Then if you look at the volume of this cone, then you'll see that it's 1 over n times this product, right? And it's precisely the product from this problem number 5, right? So you can restate this problem as follows. If the volume of this cone is independent of the direction, is it true that the body is an ellipsoid? And from here you can immediately see what happens when you apply linear transformation. So when you apply linear transformation to this cone, the volume will get multiplied by the determinant of this transformation, right? That's why we have what I wrote before. Okay. All right. So what is known about these problems? So the two-dimensional case is settled for both of them. So for problem number 8, the answer is affirmative in the two-dimensional case. It was shown by Petty. And for problem number 5, the answer is actually negative in R2. So there are bodies which are not ellipses, but satisfy the condition of this problem. And moreover, these bodies can be made arbitrarily close to the unit disk. So let me show some examples. So if you construct your body K as follows, so take P and Q greater than 1, satisfying this condition, and then in the first quadrant and the third quadrant, the boundary of K will be the boundary of this LP ball. And then in these two quadrants, 2 and 4, the boundary of K will be the boundary of this LQ ball. Okay. Now let's see what happens if you take a section perpendicular to any direction. So you will need what? You will need this is theta. So the support function in the direction of theta is the support function of this LQ ball, which is what? Which is 1 over the radius of the LP ball, right? Because of the duality, right? And the section in this direction, it's precisely 2 times the radius of the LP ball, right? So so the constant C will be just 2, right? And obviously by taking P and Q close to 2, you can make this body K very close to the Euclidean ball, right? Like this, chuk, chuk. So closer and closer. All right. So what we will proven in this talk is the following. We'll show that the answer to problems 5 and 8 is affirmative in a small neighborhood of the Euclidean ball with respect to the Banach-Mazur metric. Okay. Okay, so let's start with some observations. So first of all, we can apply a linear transformation to the body K, and we can assume that the constants in the conditions of problem 5 and problem 8 are equal to the same constants as we have for the Euclidean ball. Okay, that's first assumption, and the second assumption is that we can say that K contains the Euclidean ball of radius 1 minus delta times r with small delta, and is contained in the ball of radius 1 plus delta times r for some r. But actually, using the conditions of these two problems, one can check that this r is close to 1. So we can just erase it from here. And so we'll have that K contains this ball of radius 1 minus delta and is contained in the ball of radius 1 plus delta. So in other words, we'll assume that K is close to the Euclidean ball in the Hausdorff distance. And also one more thing, everywhere in this talk, I will assume that the average values of hk and rho k on the sphere are equal to 1. They're not actually 1, they are close to 1, but just to avoid lots of constants, I will assume that they're equal to 1, just to simplify the presentation. Okay, so let's talk about Busemann-Petty problem number 5. So I'll need some tools. I'll start with the Radon transform. So what is it? You have a Radon transform on the sphere. So you have a function f on the sphere, and you integrate it over the sphere intersected with this hyperplane, theta perp, right? So if you do it for all directions, you'll get a function on the sphere, and it will be called the Radon transform of this function f. So this measure sigma is the Lebesgue measure on this subsphere, normalized by this condition. Okay, it's a probability measure, and this gives us that the Radon transform of the constant function 1 is equal to the same function 1, right? Okay, so how do you write the areas of sections in terms of the Radon transform? It's like this. It's up to some constant. It's the Radon transform of the radial function to the power n minus 1. So the condition of Busemann-Petty problem number 5 can be written as follows. Support function times the Radon transform of rho k to the power n minus 1 is equal to some constant. But as we said, let's assume it's the same constant as for the ball. And for the unit ball, it's going to be 1, right? The support function is 1, the radial function is 1, the Radon transform of 1 is 1, so C is 1. So we'll assume that C is 1. And we arrive at this condition, right? This is our condition. So in the left-hand side, now let's, instead of K, let's put L. And think of this as a mapping that assigns to a body K another body L by this formula. Okay. So now, if we can show that the distance from L to the Euclidean ball is less than mu times the distance from K to the Euclidean ball, with mu less than 1, then we're done. I'm not specifying what distance I'm using here. You'll see later that the natural distance is the L2 distance. And then we're done. Why? Because if we use K equal to L, then we just get this condition, right? Distance from K to the ball is less than or equal to mu times the distance from K to the ball. And since mu is less than 1, this clearly implies that the distance is 0, right? This is the goal. We want to find something like this, such a contraction. Okay, our goal is to find this contraction. So where does it come from? So as you'll see, it comes from the nature of the eigenvalues of the Radon transform. So if you linearize, so this is the right-hand side of our equation, right? If you linearize this right-hand side, you get this. And gamma is the second order term. It's actually small. It's quadratic in row k minus 1, and this is less than delta. Okay? So you can estimate this gamma as follows in the L2 norm. It's delta, which comes from here, times the L2 norm of row k minus 1. Okay, so it's small with respect to the L2 norm of row k minus 1. This is what we need. Okay. So our equation becomes like this. So I will, for brevity, I will denote by this script m the Radon transform times this constant, negative n minus 1. Okay, so we get this equation. So what do we know about the Radon transform? It acts as a multiple of the identity on spherical harmonics of order m. And we can compute these coefficients explicitly. Okay, these are known coefficients. So mu2 is equal to 1, mu4 is equal to negative 3 over n plus 1. It's already less than 1. And then the rest of the coefficients are even smaller, and they go to 0 as m tends to infinity. All right. Let me see. There is something in the chat. No? Okay, so we know its coefficients. So let's look at this equation. So for the moment, I want to simplify this equation. So let me assume that instead of hk, I have rho k in this equation. In other words, I have this equation. And moreover, let me assume that rho k doesn't have a second harmonic in its spherical harmonic expansion. So with these simplifications, I can get what I want. So the L2 norm of rho k minus 1 from here can be estimated from above by the L2 norm of this operator applied to rho k minus 1 plus this small term gamma, right? Now, in rho k, as I said, we assume that we don't have a second harmonic. So we start with the fourth harmonic here. And the fourth coefficient is 3 over n plus 1, right? It's the largest coefficient in the remaining terms. And this is small. This is for the C delta times L2 norm of this. So if you combine these coefficients, you'll see that you'll get 3 over n plus 1 plus C delta. If delta is small, then this coefficient is less than 1, right? And this implies, as I explained above, that rho k is 1. Okay. So done. We solved the problem, but we made two assumptions, right? We didn't solve the original problem. We replaced hk by rho k. And second of all, we ignored second order harmonics. Let me explain now why this is not a problem. So how to deal with second order harmonics? To take care of them, we'll use the isotropic position. So we can assume that after applying a linear transformation, we can assume that k satisfies this condition. So delta ij is equal to 1 if I is equal to j, and if I is different from j, this is 0 for some constancy. And if you apply this linear transformation, K will still be close to the Euclidean ball in the Hausdorff metric. So now let's take any second order harmonic. Okay, it's a quadratic polynomial with this condition, since it's harmonic, right? The sum of I is 0. And now let's integrate this harmonic over the body K. Since K is in the isotropic position, the integral of xi xj will be 0 if I is not equal to j. But if I is equal to j, we'll just use this condition, right? The sum is 0. So this integral is 0. And then passing to polar coordinates, you can write it as the integral over the sphere of this product, meaning that rho k to the power n plus 2 doesn't have second harmonics in its spherical harmonic expansion, right? So rho k to the power n plus 2 doesn't have second harmonics. What can we say about rho k itself? We'll see that, well, it can have a second harmonic, but it will be small. So again, linearizing rho k to the power n plus 2 near 1, we get this, and this is the second order term, which is small. Now let y2 denote the second order harmonic of rho k, taking the L2 norm of both sides here and projecting and keeping only the second harmonic in the left-hand side, we get this inequality. So this means that the second harmonic of rho k in the L2 norm is small. It's very small, right? So as you can see, this is not a problem. So above, I ignored second order harmonics, but they don't create any problem. Also, I replaced rho k by hk by rho k above. But again, we'll see that this is not a problem. They are close to each other in the L2 norm. So how to do that? So let's look at the spherical harmonic expansion of hk. And let me denote these harmonics from 1 to L by eta, and the rest from L to L plus 1 to infinity, I'll denote by nu. So I'll refer to these as the head and the tail. Okay? Head and tail. We'll prove this crucial proposition that if you have any epsilon and L, then there is a delta such that if k is close to the Euclidean ball, unit Euclidean ball in the Hausdorff metric, then we have this inequality. We have this bound for the difference of hk and rho k. So this bound is trivial, but from above we bound it like this. So it's the L2 norm of the head times this epsilon and the maximal function of the tail. So this maximal function, hardy little maximal function, is defined as follows. So you have a vector E on the sphere. You take the absolute value of the function nu, you average it over the cap centered at E of radius theta, spherical radius theta, and then you take the supremum of all these numbers. Okay, so this is called the maximal function. And the fact that we'll use here is that this operator is a bounded operator from L2 on the sphere to itself. Okay. So now, how do we prove this statement over here? So you can think that everything is two-dimensional here. So I want to estimate this difference. So this is the vector E, this is the radius of the body in this direction. So if you draw this supporting line and look at the vector perpendicular to this supporting line, you get this vector E prime. So from this triangle, you can find this relation. Rho k of E is the same as the support function in this direction, E prime, divided by the cosine of this angle, right? So if you drop this cosine in the denominator, you get this inequality, right? hk of E minus hk of E prime in this direction. So what we do next, we need to estimate this from above. So we need to basically estimate this this difference here, right? This is precisely the difference between these between the support functions in these directions. What we do, we estimate this difference by the average of such distances over this spherical cap of radius theta. Theta is the angle between these two vectors, right? So we estimate it by the average of this difference on this spherical cap. Well, the rough idea is that this difference cannot be small everywhere. If it's small here, then it will be large here. That's the rough idea. And you can, so now this cap is centered at E prime, but you can replace it by a larger cap like this, centered at E. The integral will just become bigger, and here you can just put a new constant. Okay, so you replace it by by this integral, and now once you have this, you can bound this integrand as follows. So I take the head, this function eta, and I take the tail. So for the head, I will use the mean value theorem and then Bernstein's theorem. And for this, I can use the bound. E and E double prime are not far from each other. They are bounded by something of the order of root delta. Okay, so this is the first term here. And for these two terms, you can bound them by the maximal function, right? So you can bound this like this, obviously. And then if you integrate this term over this spherical cap, you can bound this by the maximal function of nu at E. Okay? So putting all together, so if delta is very small, right, you can make this as small as you want, less than epsilon. So this gives you epsilon times the L2 norm of the head, and then these two terms here give you the maximal function here. Okay, so this is what I wanted to prove. So what does it give us? We have this inequality, right? As I promised, immediately, if you apply the L2 norm, you get this. And as I said, we can use the fact that this operator is bounded. We'll get this inequality, and we're almost done. So we showed that this difference is small, but the last step, we need to compare it to the L2 norm of rho k minus 1. And again, this is not difficult. If you write rho k again as a sum of spherical harmonics, phi will be the terms from 1 to L, psi will be the terms from L plus 1 to infinity. Then what do you get? We already had this inequality above, right? We proved it above. So if you project the left-hand side to the subspace of harmonics of degree from 1 to L, you get this inequality. And if you project it to the subspace of harmonics from L plus 1 to infinity, you get this inequality, right? And from here and here, you can estimate the L2 norms of eta and nu. So for eta, you get this. So this is a small term. The main term is here, right? But actually, since in psi we'll only have harmonics of order greater than L, we can bound it by the L2 norm of psi times the maximum of these coefficients, right? But these coefficients, they go to 0. So this maximum is very small here, right? And by choosing delta also small, you can make this these coefficients as small as you want, less than epsilon, right? So nu is less than epsilon times this L2 norm. And for eta, you use a similar estimate, except for eta, you now have harmonics of degrees from 1 to L. So mu doesn't go to 0, but it's bounded by 1, right? It's bounded by 1. So for eta, you also have this inequality. And so what you showed, starting from this, you can bound the first term like so. And the second term is small because it's the tail, right? So this difference is also small with respect to this L2 norm. Okay, so I achieved two goals. So I showed that dropping the second harmonic is not a problem. It's small anyway. And then the second goal was to show that replacing HK by ρk is not a problem as well. They're close in the L2 norm. Okay, and this is how you formally write it, right? So the final solution is like this. You want to estimate the L2 norm of ρk minus 1. You break it into several pieces like this. Subtract HK, add HK, subtract this term, add it here, and so forth. So this is small, as we just showed. This is also small because it's the second order term. This term is bounded by this constant, which is less than 1 times this L2 norm. And the second harmonic is also small. Okay, so combining all these coefficients, you get some number mu, which is less than 1 if delta is small enough. Okay, and this yields what we need. This implies that ρk minus 1 is 0. Okay, so that's the basic idea behind the solution to problem 5. Now let me briefly explain how to use the same ideas for problem number 8. As you'll see, it's very similar to problem number 5. So for this problem, we have this equation, right? Curvature function is equal to n plus 1 first power of this Radon transform. Again, I assuming that the constant c is 1. We'll do the same thing. We'll linearize the right-hand side. Here we have some second order term, which is small, as we had before. All right. Now let's assume that HK is of this form, 1 plus phi, some small function phi. We'll use this notation. So this operator delta tilde is defined as follows. So you start with the function phi, extend it to Rn as a homogeneous function of degree 1, apply the usual Laplacian on Rn, and then restrict this back to the sphere. Okay? So this is what delta tilde is. Now, if the support function is of class C2, then how do you compute this curvature function? It's the sum of principal minors of the Hessian of the support function restricted to the sphere, right? So if you start with HK in this form 1 plus phi, then you can linearize this as follows. So you'll have 1, then the linear term in phi will be of this form, delta tilde of phi, plus terms of order 2 and higher. Okay. So, well, this is true if HK is in C2. We didn't make such an assumption. We're treating the general case. But later on, you will see that this is actually true, that it's in C2. Okay. All right, so we linearize Fk like this, so we end up with this equation. Left-hand side, right-hand side. Again, as before, if we ignore this term here, then we get a simpler equation. So what do you do with it? So if you ignore this term, you get, so this is gone, phi is HK minus 1, and then you can cancel 1 from both sides, invert this Laplacian tilde, and you end up with something like this. And this is very similar to what we had in problem number 5, right? We have some operator here and a small term here, right? So what do we know about this operator over here? It has the same properties. So it acts as a multiple of the identity on spherical harmonics of order m, and you can compute these coefficients. So mu2 is 1, as we had before, and the rest of the coefficients are less than 1, and they approach 0. Okay. So this is actually a contraction on harmonics of degree greater than 4, and this term is small, as before. So we're exactly in the same situation as problem number 5. Now the problem is I removed one term, p of phi, right? So I just removed this term. So what do we do with it? Of course, we need to solve this. This is the original equation. Remember, p of phi contains derivatives, products of derivatives of second order derivatives of phi. So let's denote the right-hand side of this equation by 1 plus g. And so we need to solve this equation, right, for phi. This is what we want. We'll do it like this. So we'll create a sequence phi m recursively like this. We start with the function g, solve this equation, get a function phi 0, then plug it in the second equation, get another function phi 1, and so forth. So we'll see that this sequence converges to some function phi in C2 alpha, and this function phi will solve this equation that we want. Okay, I still have, I think, a couple of minutes. So to show this convergence, observe that we have, from the definition of phi m, we have this recursive equation here. So, and you can estimate the C2 alpha norm of this difference by the C alpha norm of the right-hand side. And also you can estimate this by the C2 alpha norm of this difference for small lambda, but this is possible if you choose delta sufficiently small. So what you get is the following. This difference is estimated in terms of this difference, but then you can estimate this in terms of the difference phi m minus 1, right? And doing this m times, you arrive at this. Okay, you arrive at this. Now, since lambda small times lambda capital is less than 1, you see that we have a sequence which is convergent in C2 plus alpha to some function phi. This function phi solves this equation, which is what we needed. And to summarize, we have phi 0, which solves this Laplace equation, right? Which is the simplified version of this equation. And phi solves this Monge-Ampere equation. Now, we can use phi 0 instead of phi for our purposes, provided that this L2 norm is very small. And it's indeed very small, right? So let's look at this. Using the same estimates as we saw above for the L2 norm, we get something like this. And then adding all of them, so you write this as a telescoping sum, add all of them, you get this geometric series, compute this geometric series. It's like this, right? But you can make this as small as you want by taking lambda sufficiently small. Okay? And so this difference is very small, and we're done. Proceed as in problem number 5. And thank you very much. I'm done.